seen the construction of electromagnetic lenses, and it is established that the electromagnetic lenses behave similar to optical lenses. Let us try to understand how the image is formed in an electron microscope. What is the function of the lens? What are the different planes that you need to be aware of? And most importantly, when I talk about image formation, I'd like to draw your attention and create an impression that image that you form using any recording media, be it a photographic camera or be it a microscope or be it an electron microscope or a transmission electron microscope or scanning electron microscope, you are storing information as a distribution in a tabular form, and each pixel within an image contains some information about the intensity. And the reason why this intensity variation comes in is a consequence of the interaction that has happened within your recording media. Like I was mentioning, it could be any kind of a camera or it could be a microscope. Now, my objective in this particular lecture is to show you how an image is stored and how the image is formed, and how do I understand this image in terms of the interactions that happen just within the lens in a microscope. I'm still not going to introduce the interaction between the electron beam and the specimen yet, but just within the lens, as an electron beam is propagating, what kind of changes happen and what is the consequence of this. Also, we'll look at how a general image looks like a simulated image, and what do the intensity distributions in this image mean, and how do we relate it to an electron microscope. So before I move further with understanding how the lens functions, let me just draw your attention back to a simple ray diagram of a compound microscope and recollect the simple refraction rules for lenses. You know that when I have a lens, a convex lens in particular, what it does is any incident ray traveling parallel to the principal axis will actually refract and it will go through the focal point of the lens. Also, the opposite, that is, any ray traveling through the focal point through the lens will go parallel to the principal axis of the lens. The next thing is any ray going through the principal axis would go undeviated. Now, what you can see is the position where I place my object is called as the object plane. The position where my focal planes are called as the focal plane, and for any lens you have the two focal planes. Typically we call this as the back focal plane. Now, depending on where you are positioning your sample with respect to the lens, the image that is formed would differ. And also, once the ray goes through the focal plane, it forms an image at the image plane. So, for any lens, you have the object plane, you have the focal planes, and you have the image plane. And when you have a compound microscope or when you have an electron microscope where your electromagnetic lenses are analogous to optical lenses that you see here, the positions of where each of these lenses go into, whether they are coinciding with the image plane or the back focal plane, it plays an important role in achieving the high resolutions and in retrieving the image you get from the electron beam and specimen interaction. So let us start by looking at how a simple lens functions, and let us understand what happens at the object plane and the focal plane. Now, let us look at a simple lens, a simple convex lens. I'm not drawing the complete convex lens, but I'm just representing a lens with an arrow here. So, like I was mentioning, if I place an object, the light or the electromagnetic radiation from this goes through the lens and it converges at the back focal plane. Now, if I move the object close to the other focal plane, like in the case you have in an electron microscope, from each of these points on the specimen, you would have information propagating through the lens and going through the focal plane. Now, if I take another ray which is parallel to this particular ray from the other side of the lens, and let us say this is at some angle alpha. When this alpha reaches the maximum value of alpha, this is called as the numerical aperture of the lens. It is essentially the largest acceptance angle that you have for any lens. Now, what you can notice here is this ray 1, which is traveling this path, has a different length from the other ray. So, the ray 1 travels a different path from the ray 2, and the additional path that ray 1 travels can be given by a small path difference. Now, despite the path lengths being different, both the rays are collected more or less at the same time on the back focal plane. They further travel and then they form an image at the image plane. We will not go there yet. But what I want to impress upon you here is, suppose this length is f, and let us say my object has a height x, and let us say the distance here on the back focal plane, I give it as some value k. For each and every x in my spatial domain or in my object plane, I have a corresponding intensity k here, and all of these, if I draw the parallel lines, they would have different path lengths. Now, let us understand how these path lengths together contribute to the intensity distribution at the back focal plane. So, let us say I give the amplitude of all these as some ak. Let us say the intensity at the image plane as Ix. Both of these Ix and ak are essentially related, and in an ideal case, you should have 100% information transfer from Ix to ak. Now, before I relate these two, let me simply understand how this path difference d in terms of this angle alpha is. So, if you look at this simple triangle here, I can always write d over k is sine of alpha, and over here I also have an alpha here. X over f is also, it's actually tan of alpha, but for the low angles that we are seeing, it is approximately sine of alpha as well. Now, I was mentioning that each and every point in the object plane should contribute to formation of some kind of an image or a pattern on this back focal plane as well. So I can essentially relate all these AKs at the back focal plane, and if I sum all of them up, I should also get the intensity in the real space or intensity in the object plane as well. And if you look at it, these are sort of sinusoidal waves which are propagating, and there is an extra path length that is traveled here. So if I want to write the wave equation for a sinusoidal wave which is propagating here and here, it has a form A of k sine of 2 pi by lambda over k, where lambda is the wavelength. Sorry, it's not k here, it is 2 pi by lambda. If I say the d is the path difference here, I can write this d as the phase shift that is caused by the extra distance that this is propagated. And if I sum all such sine of 2 pi over lambda d's here together, I can get the intensity distribution at the object plane. Now, if I use this relation for x by f is sine alpha and I plug that value for d here, I end up with an expression of the form I of x is sigma a over a of k sine of 2 pi kx over lambda f. Now, if I look at this in a continuous form and I integrate it over all the frequencies here, so this particular k corresponds to the frequency in this kind of a sinusoidal waveform I write. So essentially what I am doing here is this summation has the form of what is called as a Fourier transform, and what this tells us is for any variation in the spatial domain or in the object plane for a lens, if it is propagating through the lens at the back focal plane, I can relate it with a mathematical form which is a Fourier transform, and essentially I can switch between the spatial values and the frequency values here. So this is what a Fourier transform does, and within an optical microscope or an electron microscope, please bear in mind that this particular relation of the object plane and the back focal plane can be related through a Fourier transform. And why is it important, or where is it important in an electron microscope? In an electron microscope, when these angles of deviations are extremely small, these are typically of the orders of a few milliradians, say typically 10 to 20 milliradians, and if you apply the Bragg's law here, so if you know the Bragg's law, it says n lambda is 2d sine theta. For very small angles of lambda, for very small angles of theta, which is of the order of 10 to 20 milliradians, all my planes within a specimen which are satisfying the Bragg's law are nearly paraxial and parallel to the optic axis, and all these would now converge and form some kind of a periodic pattern at the back focal plane. So essentially, the information from a crystallographic sample I get from the real space can be related to what is called as the reciprocal space at the back focal plane of an objective lens. And this is what happens within an electron microscope, and this is the function of a lens. So essentially, a lens transforms the information you get in a spatial domain to a frequency domain. Now let us understand how this looks like. If I look at the lens again and I place the so if I look at the ray diagram of this again, the information from the object plane, if I call this as x comma y, this becomes a Fourier transform of x comma y in terms of, let me write the reciprocal vectors here. So let me call it as u comma v. And when I form an image again, I actually create an inverse Fourier transform of whatever information I have at the back focal plane, and I form this at the image plane. And when I look at the information stored in an image, I was mentioning that you can consider an image is a two-dimensional distribution of intensity, and we know that for the electron beams that are used in an electron microscope, you can always represent them as psi of x comma y comma z is some psi naught sine of kx so this is the general form that you can write for any electron beam propagating with an electron microscope. So when I form an image, I am essentially transposing it to the Fourier transform at the back focal plane, and these again form an inverse Fourier transform at the image plane. So you can look at lens as a mathematical operator which switches from the spatial domain to the frequency domain, and an inverse Fourier transform from the frequency domain again to the image plane. So with this background, if I now start looking at how a periodic sinusoidal waveform looks like, let us try to see how an image is formed and how do you interpret these images. To start with, let us look at a simple tabular column and understand how a simple image is formed and stored. So for this, I give you a simple example of some values displayed in a table here. So you can see that there is a 16 cross 16 array here of ones and zeros. If I assume that these are different pixels recorded on a detector and the information stored here is either a 0 or a 1, this kind of an image is called as a bitmap image. And if I display this as a distribution of intensity, with 0 being a minima and 1 being a maxima, I would end up with an image like this. I see a simple checkered board pattern. So this is a simple black and white image. So what I want to impress upon you here is, when I have an image, no matter which mode I am recording it from, I can store the information as variations of some intensity within each pixel of the detector that I am using. Now let us complicate this a little bit more. Here is the most simplified case of a bitmap image. If I store this numbers at each pixel with values between 0 to 255, I construct what is called as a grayscale image. Now, if I have a grayscale image, this is what I record in typical electron microscopes. I have these intensity values ranging from 0 to 255, and let's take a look at a slightly more complicated version of an image. So I now have a 64 cross 64 array here. So let us say the intensities have different numbers here: 69, 197, 212, and 172 here, and 198. If I assume that at each of these pixels there is some value of intensity recorded, this appears as a grayscale image like this. Now, why do I want to show this? Each of these grayscale images now, if you remember, if I have an object which is having information stored like this, or if an object has variations within the object like this, if I pass this through a lens, at the back focal plane, I should see a Fourier transform of this. Now, before I look at a Fourier transform of this kind of an image, let us try to understand how we see something in an electron microscope and how the intensity variations look like with a simple unidimensional sinusoidal waveform. So, how do we see something in an electron microscope? Like I was mentioning, a generalized equation. If I draw a simple periodic notation of an electron beam in one dimension, you can write it as psi of x comma t is psi naught sine kx minus omega t. And within a microscope, you are recording information averaged over time, typically in the order of a few milliseconds or a few seconds. And in this particular scenario, the information I record is averaged over this period of time. So as you have time averaged information, there are techniques these days where you can also use pulsating beams, and you can use a laser and a microwave interrupted kind of an imaging, where you can do ultra fast imaging in microscopes. I'm not going there yet, where the time component cannot be ignored. But for an averaged image for a regular conventional TEM, you can write this as a simplified version at a given instance of time as psi x is psi naught sine kx. Now, in reality, if I represent this as a wave, I see it as an equation which appears like this, as a graph which appears like this. But if I stack multiple such sinusoidal waveforms, so let us say I'm trying to form an image where my x is 0 here and x is, say, some 128 here. If I add 128 such sinusoidal waveforms, one next to the other, it appears like this. So I've just simulated a simple image with a periodic waveform, and to understand how this looks like and what is the relation between this and this kind of an image, if I take a histogram at the middle of this, and if I take a histogram at any position on the y-axis of this image, I end up with a graph which looks like this. As you can see, this is a grayscale image, and this is a 1400 cross 1400 pixel image, and at the middle here I see the maxima is approximately 250, I don't know, 252 counts, and somewhere here it is around 112 or 115 counts. So essentially, what you have here is a band of fringes the way you see from a double slit experiment, and this has a periodic or a sinusoidal waveform. Now, if I write this with an extremely simple notation as psi x is psi naught sin kx, let us see what happens to this image when I vary each of these parameters. When I represent a wave with this kind of a notation, I call this as the amplitude and I call this as the frequency, or this term entirely inside here is called as the phase of the sinusoidal waveform. Let us see what happens when I change the amplitude and when I change the phase and how these images change. So, if I look at these two images, you can see the image on the top is appearing a lot more brighter than the image on the bottom. So, if I take the histograms of these two, the image on the top has an amplitude of psi naught, whereas the image on the bottom has an amplitude of psi naught over 2. So, the maxima here is 250 plus and the maxima here is 120 plus. So, essentially a periodic sinusoidal waveform appears like this, and now in this particular equation, if I play with the phase, what happens is the following. So, the image on the top has a frequency where I have a limited number of maxima and minima within a given width, whereas on the bottom the frequency is a lot more. I have more number of these maxima and minima, the crests and troughs in the periodic waveform here. So, if I look at the sinusoidal wave notation, the image on the top can be represented as psi naught x and the image on the bottom can be represented as some psi naught sin 4x. So, within the, I can write it in two ways. I can say that the frequency here is 4 times more than the frequency on the top, which means within the same period I have kind of fixed in 4 more sinusoidal waveforms within the given value or within the given period, or the wavelengths of these two can be considered different as well. Now, let us not go there yet, but essentially the idea is I can play with the period, I can play with the frequency here, which is in turn changing the phase of my sinusoidal waveform, and that gives me this kind of an image. Where am I heading to with this? This is the most simplest case, and if I now complicate it slightly by showing you images like this, if you notice these three images from the first visual comparison that I can draw, they all look extremely similar. But if I look very carefully at the bottom left hand corner of each of the images, the width of these is not exactly the same. So, one way in which I change the phase in the previous images or the previous example is by changing the frequency there, but here I have introduced a small phase shift. So, if I look at it, if I take the histograms across these three images, with respect to a fixed point, there is a small phase shift which has happened, and if I write the sinusoidal wave notation of these again, here it is psi naught x, it is psi naught x plus pi by 3 and it is psi naught x plus pi by 6. So, these are simple unidimensional sinusoidal waveforms, and you can complicate this a little further. How do I complicate it? Now, I have only seen the sinusoidal waveform in one dimension and I did not modify it, and I only assume that along the x axis only there is a variation in the sinusoidal waveform. If you look at this image, you can look at it as again a periodic waveform, but can we still represent it with an equation which is of the form psi x is psi naught sine kx? The answer is both yes and no. I can simply take two components and get two intensity values in the x and y directions, and this would give me a varying sinusoidal waveform with some period like this, or it would give me a sinusoidal waveform with some period like that. Or what I can also do is I can assume this is similar to the previous case with the wave front slightly rotated. So what do I mean by wave front? So if I draw a plane normal to the propagating wave front, so this is my direction of the wave front. It is slightly rotated from the x-axis, and if you measure this angle, in this case it happens to be 30 degrees. If I give this wave vector or the wave front as some vector k bar, I can now modify this equation by writing as psi of x comma y is psi naught sine of k bar dot r bar, where I can write this r bar as the position vector and k bar as this particular wave front, plus some value of phase psi naught. I can also decompose it and write it in terms of two different wave vectors, both represented along the x and y directions, as here. If I write this as psi x is psi naught x sine mx, this would become psi y is psi naught y sine ny. These m and n's can be different. Now what am I trying to achieve here? I am trying to show you that within an image you can represent it in terms of some kind of periodic waveforms, sinusoidals, in both the horizontal and the vertical axis, or in other words in the radial axis here, with changing amplitudes and changing frequencies. Now if you recollect the simple operation of the lens that I showed you some time ago, if I have a complex image like this and if I pass it through a lens, essentially if I take an image from the back focal plane, what I can do is I can decompose this image into three different parts of three repetitive sinusoidal waveforms, and if I take a pattern of this from the frequency domain, I can look at these three sinusoidal waveforms having some kind of an equation like this. I can represent psi xy as psi naught sine k1 dot r, this is some psi naught k2 dot r, and this is k3 dot r. And as you can see, my frequencies for all these three are changing. My amplitudes also slightly fluctuate here if I take the absolute values here. But essentially, what I end up with is some kind of a composite convolution between three periodic sinusoidal waveforms. Now, this kind of a knowledge, I can extend it to any image that I see, and I obtain what is called as a Fourier transform at the back focal plane. So when I take an object and pass it through a lens, at the back focal plane, I get the Fourier transform of the particular image, and then from the back focal plane, when I take it back to the image plane again, I take an inverse Fourier transform. So with this, I'd like to conclude this particular lecture. in stating that when I have an image consists of a spatial variation of intensity, and at each pixel, if there is a periodicity in the image, no matter even if there is not any periodicity, I can decompose this image into multiple components of periodic sinusoidal waveforms. And when I take the information at the back focal plane, what I get is a Fourier transform at the back focal plane. And within an imaging system, within a microscope, if I go from the back focal plane again to the image plane, I do an inverse Fourier transform on the back focal plane, and I get the information recorded on the recording device. So essentially, what I can do is I can look at a microscope or a lens as a simple mathematical operator which is modulating my electron wave function, which is either entering the specimen. The specimen itself acts as another modulator, and within electron microscope, I'm trying to look at a convolution of various modulators or operators that exist, and I form an image. With this, I think I've shown you what the function of a lens is. I've tried to impress upon you that there is the image plane, there's the back focal plane, there's the object plane, and when an electron wave or light propagates through these lenses, you simply have a mathematical modulation which can be represented by a Fourier transform. We'll look at more effects of this, and what I've also not discussed explicitly here is when these modulations are happening, I'm also causing a phase shift and an amplitude change. With or without a specimen, when an electron beam is simply propagating through a magnetic lens, bear in mind that there is always a phase shift happening. And by understanding these phase shifts and by understanding how the specimen can be represented with some kind of an electrostatic or a magnetic potential, we can understand and model how an image is formed within an electron microscope. And there are different imaging modes, and we see different information that can be obtained from different imaging modes. And this is what is happening within an electron microscope. Thank you.